All right, everybody. It's like I'm teaching class again. All right, let's get going. So a few months ago, Michael Manga, who's the chair of my department at UC Berkeley, caught me in the hallway and asked me if I'd be willing to do a tutorial. And I couldn't come up with any good reason on the spot why I couldn't do it. And so here we are today. This is the problem of having your chair also be the president of one of the sections. So what he asked me to do is do a tutorial on clumped isotope geochemistry, which is a pretty broad topic. With no instructions, I've sort of come up with what I want to do and what we're going to go through. And so the first thing we're going to do is go through, I'm going to be pointing at this one over here. We're going to go through theory and some degree of history just to set the stage. I'm then mostly going to talk about carbonate clumping because it serves, I think, as a useful set of lessons of what it takes to do this, the history behind it, to bring various groups into agreement, and where, after a decade approximately of trying to do it, the field stands. And then I'll talk about overview of new systems coming online and the challenges and opportunities associated with taking this approach to new systems. All right, so I want to begin with a classic problem in isotope geochemistry to set the stage for why one would ever bother thinking about this thing, clumped isotope geochemistry, and it's to look at what Harold Urey on the left and Sam Epstein on the right were working on in the late 40s and early 50s, and that's auction isotope geothermometry. And so if we look at this equation, on the left side we've got carbonate with no rare isotopes, water with one rare isotope, substituting for a carbonate isotope log with all rare isotopes of O18 and an unsubstituted water. And you can take any given chemical reaction and assume that you are in equilibrium and write an equilibrium constant for this. And if you do this, you can, through a few shortcuts, write something of the following way. The equilibrium constant for this reaction is essentially the O18 to O16 ratio of the carbonate versus that in the water, and this equilibrium constant is a function of temperature. Right? They knew this in the late 40s, very much from theory for World War II, and Urey pushed to having this applied to geological systems. And the fundamental problem is when you look at something like this, is that you've got one equation, all right? You want to know temperature, or you want to know the isotopic composition of the water, but you always have two unknowns when you go in to make a measurement. You can measure the auction isotopic composition of a carbonate, and you have to make some assumption, either about temperature or about the fluid, to get the other one. All right? And so this has always been an issue in play, and still is an issue when you do auction isotope thermometry. Right? And over the years, there's been an enormous number of ways to get around this. One of which is to go and use other thermometers. And so, for example, you can go and use organic proxies, so alkanones, GGTs, things like this. You can use magnesium-calcium ratios, strontium-calcium ratios, so trace metal ratios to get temperature. Harry Elderfield has pioneered this very much for benthics and things like that. You can do dual auction isotopes, so look at two different phases, phosphate and calcite, or in silica, and try and do thermometry this way. And what we're going to focus on today is another approach, right? And that's to do clumped isotope geochemistry. Has advantages, has disadvantages, and I want to go through both aspects of the double-edged sword. All right, so what is clumping in carbonates? We're going to do the exact same thing we just did a moment ago for auction isotope thermometry with water in carbonates and look at the clumping reaction. So take the following reaction. What I've underlined here just to put us on the same page is all the rare isotopes. So here we have carbonate with one O18, carbonate with one C13. If you react these things together, at least in an equation like this, you get a carbonate that has two rare isotopes, C13 and O18 together, and a carbonate that has no rare isotopes. Now, in the solid state, you can actually have this happen at high temperature, but in fluid systems, this is not going on, but it is a reaction. And so by rights, if we write down a chemical reaction, we can write down equilibrium constant for it and think about thermometry. And it turns out, for equilibrated systems, at all conditions, except infinite temperature, you will shove yourself to the right. Right? At equilibrium, the system tends to prefer to be on the right side of this equation, to have the two rare isotopes together. And at colder temperatures, you're pushed more to the right. At warmer temperatures, you're pushed less to the right. But you're always going towards the clumped isotope reaction. And so this is the clumped isotope log. And the key thing here is just the statement that when you look at this, and we'll look at this in more detail in a little bit, is at isotopic equilibrium, systems tend to favor distributing heavy isotopes together. That is not a law, all right? There are examples where this is not true. But it's a tendency, and if you catch me on the street and give me a random reaction and ask me to predict something, this is what I will predict. But there are examples of anti-clumping, all right? So it's not universal. But in carbonate, this is true. Right, and so systems tend to clump, and this is the idea of clumped isotopologs, clumped isotope geochemistry, that you put two rare heavy isotopes together. Right, so let's look at this reaction a little more carefully. So I'm just writing the exact same thing we looked at a moment ago. Let's write the equilibrium constant for this. So in this case, we have the products, the right side in this case, over the left side. So the doubly substituted species, the clumped isotopolog, the species with C13 and O18 is on the top here. On the bottom are the singly substituted species, and here's the unsubstituted species. And the key thing is, just like we looked at a moment ago for oxygen isotope thermometry, we can write an equilibrium constant for this. This equilibrium constant is a function of temperature, as they tend to be. But unlike the reaction that we looked at with water, everything in here is carbonate. All right? There is only one phase that we're dealing with. It's a homogeneous phase. Equilibrium constant and thermometer. And this is where the difference is between oxygen isotope thermometry and clumping. Same thermodynamic principles, except we're looking at one thing. And so you can look at predictions. This is from a paper from Edwin Schaubel and others in 2006. You can look at how much are you going to clump, how does the equilibrium constant vary as a function of temperature, and you can see over here there is a variation. At very high temperatures, you have less clumping. At very low temperatures, you have more clumping. And you're going here to an equilibrium constant infinite temperature of 1, in which you are distributing the clumping. The equilibrium constant has no dependence on the left side or the right side. And these are small numbers, 1.0005, right? So 0.5 per mil is the total range over the nominal thermal range that you might be interested in for low temperature processes up through igneous processes. And people have now, for 13 years, gone and tried to show this is true and understand what's happening. And this is an example of measurements in things where they're made at a known temperature versus a function of temperature. And so you get a similar kind of relationship where you have higher amounts of clumping at lower temperatures, less amount of clumping at higher temperatures. And this is a review paper from Sierra Peterson going through a bunch of labs that have done this approach to show that there's nominal reproducibility between groups. All right, so what I want to first do is demystify this. All I've done so far is make assertions. I've asserted that clumping is favored and that we can do these things. And I want to take a moment is to go through why this is the case, just so it seems a little bit less arbitrary that people state this. And the system I like to work on and think about when I explain this is not carbonates, not more the complicated species. It's hydrogen, in part because hydrogen gas, in part because it's simple, and there's an interesting, as I'll go through, historical aspect to this. All right, so let's take the following reaction. 2HD, so here is a hydrogen molecule, H2, that has one rare isotope deuterium, reacted together to make H2, no rare isotopes, and to make D2 with two rare isotopes. So in this case, this D2 is the clumped isotopic species. And this was interrogated theoretically in the early 30s by Harold Urey and Dave Rittenberg, wrote a paper in which they examined the thermodynamics of this. Right? So they were looking at clumped isotope reactions very early on, in part as an understanding of statistical and quantum mechanics as it was coming online in the US. Right? And so what you can do is take this reaction and do as we did a moment ago and write an equilibrium constant for it. The equilibrium constant is H2 times D2 over HD squared. And we can do a little trick here and ask ourselves, what is this kind of equal to? And let's make the assumption that there is no desire on the part of H and D to clump. It is random. Right? You can think about doing this like coin flips. What are the chances of flipping two heads together? It's the proportion of heads, 50%, times the proportion of heads, 50%. So putting two heads together, you would have a probability of a quarter. Same thing for tails. Putting two tails together, it's a probability of 25%, or whatever their proportions are. For HD, we don't care about orientation. It doesn't matter whether the hydrogen comes first or the deuterium comes first, because you can simply rotate the molecule. And so it is 2 times heads times tails, or 2 times H times D. And so if you do this, and you do this approximation, assuming this randomness, assuming this probabilistic aspect of it, you get the following. It comes out h squared, so this would be head squared, 50% squared, d squared, okay, so two tails together, 50% squared, over 2 times h times d squared. All right, the 2 there for this orientation aspect of it. And the key thing here is if you take this through, what you can see is that all the h's cancel, all the d's cancel, and you're just left with 1 over 4. Right, so for a random distribution of isotopes in this system, the equilibrium constant is always a quarter, regardless of how much H you have or how much D you have, as long as there's a tiny bit of one of them. All right, so if it's 99% H, 1% D, 50% H, 50% D, it doesn't matter. The equilibrium constant for a random distribution is always 0.25. And what Urey and Rittenberg calculated in the early 30s is that at room temperature, this is not the case. At room temperature, they calculated the equilibrium constant is 0.3. In other words, there is an excess of H2 and D2 as compared to HD as compared to a random distribution. There's more of the D2 than you'd expect if you did this randomly. And they understood what was going on. Right? So what's happening? Why are we doing this? I haven't done anything new, just translated the problem to a simpler system. Right? And so there's a variety of ways to think about it. I'm going to do it this way, and it's a little bit of introduction to quantum mechanics. If we think about a harmonic oscillator, we make that assumption in terms of there being an energy well, and we're going to look at the 0-point energies, we can ordinate the 0-point energies of these different isotopologues. Right? So if you do that, D2 will be lowest in energy, then you'll have HD, and then you'll have H2. Right? And this is going to be true to some degree that you're going to have this order. And so let's assume the following difference in energy. All right, that there's a difference in energy of E1, what did I do over here? E2 over here, between going from HD to D2, and a difference in energy of E1 of going from HD to H2. So what you can see here, importantly, is if you take 2HD and you split them up, there's going to be a drop in energy going down to D2, and there's going to be a commensurate rise in energy of going to H2. All right? And the question for a system that wants to minimize its energy is what is the most bang for its buck? All right? Does it lower its energy by going down and up here, or by populating HD? All right, so if you imagine for a moment that the energy differences are equal, E1 equals E2, there will be no reason for a system trying to lower its free energy to sit there and stuff extra D's together as D2. And as we'll talk about in a moment, entropy will be the only energetic term that matters, and you will get a random distribution of isotopes. If, on the other hand, there is an enormous rise going from HD to H2 as compared to the drop, it's a bad deal to put two D's together. All right? Energetically, you're paying a penalty. Your energy is going up. And in this case, you would have anti-clumping. You would favor going to HD because you would lower the overall energy of the system. And this happens. There are systems in which this occurs. The more normal case is, if I get there, the more normal case in an exaggerated fashion is that the rise in energy of going from HD to H2 or going from a singly substituted species to an unsubstituted species is smaller in absolute terms. The absolute value of this energy difference is smaller than the drop of going to D2. And so systems tend to clump as a result of this. Right? And so this is, again, if you just ask me on the street to guess, this is what I will tend to guess is going on. All right, so this just says things are clumping, and if this was the only energetic contribution that mattered, you would shove everything into D2 and H2. You'd have no singly substituted species, and the key thing is there are other energetic contributions. And to do this, I want to think in terms of classical thermodynamics. So what we're looking at here is just a sketch of temperature versus the equilibrium constant. At infinite temperature, you go to 0.25. At room temperature, this is the calculation of Rittenberg and Urey, you're sitting there at about 0.3. All right, so there is a temperature dependence to this. And one way to think about this in terms of classical thermodynamics, all right, that the Gibbs free energy, the Helmholtz free energy, is a function of enthalpy and entropy, in which entropy has a temperature on the front end, and there's a negative sign. And so one way, it's not exactly right, but it's useful. One way to think about what we were talking about in terms of the energy levels before is in terms of enthalpy, right? The enthalpy of the bonds. You even think about it in terms of an enthalpy of mixing. The temperature dependence comes in dominantly from the entropic aspect of it. If you put D's together and H's together to make D2 and H2, you are ordering the system, all right? You are making the entropy of the system go down. There's a negative sign in here, and that makes the free energy of the system go up. And so you're paying another energetic penalty to putting order into the system, to order it. And it's modified by T. And so the penalty is much, much worse to order a system at very, very high temperatures as compared to doing this at very, very low temperatures. And a similar construction that I've just gone through can be done for all the isotopic heterogeneous phase thermometers, for water and carbonates, things like that. But this is the origin of the temperature dependence of the system, or a way to think about it. All right, so what's the history behind this? So Rittenberg and Urey did these calculations, and in a very short amount of time, experimental results were done with very high labels of D2, H2, of D and H, and done mass spectrometrically by Gould et al. In the early 30s, 1934, and they measured, based on the D2 times H2 over HD abundances, the equilibrium constant experimentally as a function of temperature. So in the 30s, they had a clumped isotope thermometer, all right? They could measure that at lower temperatures, you favor more D2, at higher temperatures, you favor less. And I'll just note, and this is historically interesting, but practically unimportant, in that the very first, as far as I know, isotopic thermometer that was done theoretically and calibrated to some degree in the lab was done on clumping, right? That might not be true, but that's my understanding of it at least. And so you have to wait till the late 40s and early 50s to get into heterogeneous phase thermometers. And I'll note, just this past year, this is now being done in a serious way at natural abundances, so not sticking a ton of deuterium, by looking at and measuring the amount of D2, right? And so this is someone repeating effectively the experiments done here, but at natural abundances to do D2 thermometry. So this is now, I don't know, 80 years later, we have come full circle and are back to trying to measure D2. And I'll note the clumped isotope thermometry is one of many in terms of what are described as homogeneous phase geothermometers. One that's similar, there are differences, but it's similar in at least in an intuitive sense, is the Curie point for magnetics. And so in magnetism, you go from ordered states of spin alignment to disordered states when you go to higher temperatures. This is again an entropic enthalpic issue. All right, so there is thermometry in the Curie point. Another one in terms of petrological systems is in iron and magnesium site partitioning in periodic states. It's a similar kind of thing. Very similar sorts of thermodynamics can be used to describe the phenomenon, and there are thermometers. And so it's one of many different types of thermometers that are relying on the same sorts of energetics to describe it. Okay, and so one thing I want to point out here is I've come at this from the statement of thermometry. It's a very useful way to think about clumping. I just want to say, when is clumping, if I think it would work, when is clumping not a geothermometer or paleothermometer? All right, so the basis of doing clumped isotope geochemistry for thermometry is rooted in homogeneous phase equilibrium thermodynamics. And the key thing here is equilibrium, right? You have to have a system form an isotopic equilibrium or re-equilibrate for the temperature to mean something that you want it to mean. Or alternatively, you have to have some kinetic process that gives you a relationship with temperature that you calibrate. But there are many instances in which the temperature that you would calculate based on these sorts of equilibria has no meaning as a temperature. That doesn't mean it's not useful, but it means something else. And so one trivial example is mixing. If I take two carbonates and one has a clumped isotopic temperature of 0 degrees and one has a clumped isotopic temperature of 20 degrees, I mix them 50-50, there's some interesting details in here, but approximately for a simple thing, you'll get about 10 degrees. That temperature doesn't mean a formation temperature. It is a mixture of two end members. So mixing in and of itself will mess you up in terms of these sorts of things and thinking about a formation temperature. Secondarily, kinetics matter, all right? If you have kinetics in play, you will not be recording equilibrium. And so one aspect of kinetics would be simply mass transport, in which you are diffusing things around. There are diffusive mass laws, and they will move the clumped isotopes differently. They often are a function of mass, not of zero-point energies, and also bond breakage and bond formation. And I'll note, these two things often can interplay. If you have Rayleigh distillation, you in effect can have mixing, because you're mixing things as a function of reaction progress. And so this is just something to keep in mind. When you calculate a temperature, you are making an assumption, if you're thinking about it in terms of formation, that you've formed an equilibrium, but other things can come into play that would make the temperature not be a formation temperature. And to me, this is not a detraction. This is just an aspect of these sorts of things, that these are apparent temperatures that are being calculated. All right. So now I want to move towards applications to sort of go beyond the theoretical stuff and those sorts of things to what people are practically doing. And I want to do this in the context of carbonates because it is the best studied of the systems, the best understood. It's gone through the most challenges in terms of groups, many groups trying to do it, and people trying to get their acts together to get agreement between groups, and the study of systems. And it's also built on a very long history of understanding of oxygen isotopes. All right, if there's something to be studied in oxygen isotopes, someone's probably tried to do it for clumping. And so the way this is done is generally you take carbonate in a little vial and you throw it into an acid bath and you release CO2. And this is the analyte, right? This is what you measure. You do not measure the CO3 molecule directly. You measure CO2 as an indirect participant in this whole thing, similar to the way most people, unless you're using an ion probe, would measure oxygen isotopes of carbonates. And so we track mass 47 as a mechanism to study clumping. And what we're doing when we do this is mostly studying C13O18. This is of order 97% of the signal, in which you've got C13, O16, O18 plus something over here that can be removed, and you make this species. But there are other molecules involved. You can take C13, O17, 2, or C12, assuming I did all my math correctly, C12, O17, O18. These will also contribute to the problem. And at the end, I'll note a direction this is moving where people are starting to get away from combining these things together. In the literature, you'll oftentimes see people say that they're studying C13O18 clumping to first order, maybe in second order. That's true because this is the dominant signal in the group. And as a rule, and I've done this for other things, but I wasn't involved in this part of it, when you invent a new technique in isotope geochemistry, they take you into a back room and say, you must make up new nomenclature for the sole purpose of confusing people. And that's what's done. There is nomenclature for describing clumped isotope geochemistry. And the way it's done is using Cap47 notation. And this is 1,000 times the 47 to 44 content of a sample. So how much of the clumped molecule do you have relative to 44, 12, O16, 2, so no rare isotopes, as compared to the random distribution, right? And so what this does effectively is a normalization. So if you think about the HD D2 system, we were talking about the infinite temperature, the random equilibrium constant is 0.25, and at room temperature is 0.3. And we do this in part to normalize out that kind of stuff so that we do 0.3 over 0.25. And it makes it easier, and it's no different from the way we do alpha notation, where alphas are always normalized to 1 at infinite temperature. All right, so this is what is tracked, and keep in mind is higher Cap47, higher clumping, lower Cap47, less clumping. At infinite temperature, you hit 0. Anything that is formed in equilibrium must be 0 at infinite temperature or above. If you have something that is negative, it immediately tells you you have a kinetic process, a non-equilibrium process involved in the system. All right, so what's the power of clumped isotopes? Why are people interested? Why, when this was done originally in John Eiler's group in the mid-2000s, were people excited about it? It's based on going back to the motivation. All right, so if we start with typical oxygen isotope thermometry, you have an equilibrium constant, 018 to 16 ratio of the carbonate, 018 to 16 ratio of the water. We've got 2 unknowns, but only 1 determination of the system. By doing the clumping, we go from 1 equation with 2 unknowns to a determined system. We go and have 1 unknown. If you do the clumping, you measure the temperature. You also measure the 018 of the carbonate. If you know this equilibrium constant, you can then calculate the 018 of the water. All right, so you go from being underdetermined to having a closed set of equations. All right, so you go from under-constrained to constrained. And there's a great interest in not just doing paleothermometry, but trying to get at 018 histories of water. You can imagine being interesting for evaporative systems, freshwater inputs, the history of oxygen isotopes, of seawater through time. Right? You can now have a tool to not just do thermometry, but also to get at something else that people find equally interesting. All right. So the modern start of all of this is in 2004, in which carbonate clumping was done, not on carbonates. John Eiler's group with Edwin Schabel measured it on CO2. Here would be 25 degrees. Car exhaust is really, really high. And these are observations from the atmosphere. And they were trying to get at mixing ratios of various sources of CO2 to the atmosphere. But the real push of this is in 2006, when carbonate clumping really was starting to be done. And this is an early determination of the equilibrium constant, or the clumping content, of carbonates where things were grown, or you have natural materials, corals, that seem to fall on the same line. And just to give you an example of an application, this is an early attempt to go at a really big problem, the Phanerozoic history of the oxygen isotopic composition of seawater. Here is the so-called visor curve, the 018s. These open symbols are calculations of the 018 of seawater going back in time. This is from Renata Cummins' work in 2014. We go look at an update of this from Greg Henke's, working with Ben Passy and others, doing this and looking at a whole bunch of samples. This is temperature here versus 018 of seawater. They essentially say that for most marine samples, the 018 of seawater going back to the early Phanerozoic hasn't changed. But you get this interesting thing that when you do this, the early Phanerozoic apparently had very, very warm temperatures. All right, so what are the challenges that have been faced over the past 13 years that have been overcome, I would say? First challenge in the beginning was sample size. The original sample sizes were of order 4 to 8 milligrams per sample, replicated 3 times. You're not doing benthic 4 amps. This has now gotten into 250 to 500 milligram quantities. The other thing is temperature sensitivity. A challenge of this, and this is from Nithya Thiagarajan's work, the best you're going to get is order a degree, 1 sigma, maybe half a degree. And so certain problems are not going to be easily accessed with this kind of technique. Finally, interlaboratory agreement has been an issue that has been overcome, I think, in part from people being nice and working together to really get this done. And this is a great example from a recent paper from Stefano Bernasconi. I'm just doing a comparison of measurements made at ETH in his group versus measurements made in Kristen Bergman's lab at MIT, in which you can get one-to-one effectively agreement through rigorous standardization. All right, I've got a couple minutes, so I'm going to cut this short. I just want to note that this is a double-edged sword. Right? There's aspects of clumping that have issues that are similar to 018s and dissimilar. So one thing is dissolution reprecipitation will mess up oxygen isotope thermometry, and it will mess up clumping. Solid state closed system reprecipitation will not modify 018, but if you dissolve and reprecipitate in a high rock to water ratio system, you will modify clumping. All right? Diffusion internally and movement of O around will also screw up in a single crystal the clumped isotopes, or it can, but it won't mess up the 018. Open system will do both. And so there are differences in these systems. And I'll just give an example. This is from Greg Henke's work, showing where if you leave a system at 600 degrees for a given amount of time, I have to look over here, in 10 to the minus 7 years, you will be in equilibrium. So you throw a sample of carbonate in your lab furnace at 800 degrees. By the time you get it out, you will get 800 degrees no matter what temperature you started with. And it will still be an optimal grade calcite if you did this. And I'll just note, and I'm going to stop here, what's on the horizon for carbonate clumping. One is moving to cap 48s, looking at 48 and 47 together, so looking at 2 systems. And the other thing on the horizon, there's papers coming out now, is looking at doing this spectroscopically, where you can not put them all together. You can look at single species and go after the equilibrium constant. So it's time, and so I'm happy to take any questions. All right, I will declare victory and that my job is done. I'm around, I'm happy to take any questions offline.